Hi, this is Dr. Neff, and this video is on covalent bonding, the third of our three types of bonding. So this type of bonding involves two or more nonmetals both having high ionization energy and high electron affinity. And what that means, having those properties, is that neither nonmetal wants to give up electrons. In fact, nonmetals would prefer to take on electrons, so nonmetals want more electrons. And so what they have to do in this type of bonding is share their valence electrons so that they both can get a noble gas configuration. So if we consider a chlorine atom, one way that I can show its valence electrons is in a Lewis dot structure. And so chlorine has 7 valence electrons, and so the electrons are shown as dots. That's why we call it a Lewis dot structure. So if two chlorines come together, they both have those 7 valence electrons. To be like the nearest noble gas, they each need one more valence electron. So they're going to share these 2 valence electrons in a bond. And so what that would look like is we would now draw the shared electrons as a dash to signify a bond, and we leave the unshared electrons around the element symbols as dots. So again, this dash is a bond, which equals 2 electrons. I also call these electrons that are just on one atom lone pair electrons. Lone because they're not shared. So the bond we're showing here is a single bond, which is 2 electrons. We could also have a double bond, which would be 4 electrons. And an example of that would be oxygen. Each oxygen atom has 6 valence electrons. So when 2 of those oxygen atoms come together, they're going to have to share 2 pairs. And so we can draw that as 2 lines, and then we show their lone pair electrons. So again, that's a double bond. That's going to be stronger because there's more electrons. I could also have a triple bond, which would be 6 electrons. And an example of an element that does this is nitrogen. Each nitrogen has just 5 valence electrons. Let me draw those in a slightly different way. So when 2 of those nitrogens come together, now they're going to share 3 pairs to make a triple bond, and they'll each have a lone pair. And that's going to be, that triple bond is going to be a lot stronger, again, because there's more electrons involved. So the goal of covalent bonding is a filled shell, which is equal to 8 valence electrons. And you may have learned that in high school as the octet rule. And both the examples of the oxygen and the chlorine do obey that octet rule, or both oxygen and chlorine get their filled shell. So the oxygen, I count not only his lone pairs, but the pairs that he's sharing. So there's 8, and the other guy also has 8. And the same thing for the chlorine. You look at the pair that he's sharing, as well as his 6 lone pairs, or his 6 lone electrons, and the other guy also has 8. So covalent bonds are localized, meaning that the shared electrons are held between 2 atoms. They're not spread out throughout the molecule like in metallic bonding. And they're also directional, meaning that electronegativity plays a part, where electronegativity is the pull an atom in a bond has on the electrons in the bond. So in the case of the O2, where both of the atoms are identical, the electronegativity is the same for the 2 atoms. So in that case, we say that the molecule is nonpolar, or that the electron distribution is equal throughout the molecule, or equal throughout the bond. And again, that's because each of the oxygens are pulling in the same way. But if I have something like HCl, which would look like that, the chlorine is more electronegative. So it's pulling the electrons in that bond to itself. Which results in a polar bond, which is an uneven distribution of the bonding electrons. And we can show that by drawing an arrow where the arrowhead points towards the more electronegative element. Okay. I've shown some little pictures to kind of illustrate this, where nonpolar bonds are equal sharing of the electrons, and so that's like kids that can play well together. But polar molecules are unequal sharing, so that's like kids that can't play well and can't share very well. So the way we name covalent compounds is a little bit different than how we do ionic compounds. And a lot of the covalent compounds that we'll look at are just diatomic elements, so they just are called by their element name, like hydrogen, which would be H2, oxygen, which is O2, fluorine, which is F2, and there's quite a few of those. There's just some common names, like water, which we also could name according to the systematic way I'm going to cover right now. When you have two different atoms in your molecule like you do in water, you start by using the full name of the first element in the formula, followed by the start of the second element's name with an IDE suffix. So following that, water would actually be hydrogen oxide. But then to indicate that there's two hydrogens in that molecule, I would use a Greek prefix, so this would be dihydrogen monoxide. So for example, let's say, example would be something like SO2, which would be sulfur dioxide. We leave the mono off if there's only one of the first element, but we make sure we include it if it's our second element. So another example would be O5, which would be diphosphorus pentoxide. Oops. So since the goal of covalent bonding is for both the elements involved to have a filled shell, which is typically 8 valence electrons, we'll see that there's some common bonding patterns that we see again and again. And for example, one of those is for carbon. Carbon always must have 4 bonds. No more, no less. And it can accomplish that in a bunch of different ways. It can have 4 single bonds, a double bond and 2 single bonds, or a triple bond and a single bond. But it always is going to have 4 bonds. Nitrogen is going to prefer to have 3 bonds and 1 lone pair. And where this is coming from is the fact that nitrogen has 5 valence electrons. So you can see it's already got that 1 lone pair, and those three that don't have pairs are going to form the 3 bonds. And I can go back to the carbon and show that he started out with 4 valence electrons. So that's where the 4 bonds come from. He needs to share 4 electrons with some other atom. If we look at oxygen, which has 6 valence electrons, you can see it's got 2 electrons that don't have a pair to it, so it's going to want to share 2 electrons with some other atom. So it's going to prefer to form 2 bonds and have 2 lone pairs. And hydrogen is a little unusual. Hydrogen has just one valence electron. It would have to gain 7 to get an octet, so it prefers just one bond. Because for hydrogen, a filled shell is 2 electrons. Another element that prefers just one bond is fluorine, but now fluorine will get the octet because fluorine starts out with 7 valence electrons. So it just needs to share one electron with another atom. So again, it's going to form one bond and have 3 lone pairs. And like I said, these are patterns that we see again and again. Okay, so now let's talk about some bond properties, and we'll start by looking at the bond length, which is defined as the distance between the centers of 2 covalently bonded atoms. So really what this is the sum of the atomic radii of the 2 atoms in the bond. And this bond length is very much connected to the bond order. Specifically, the bond order is how many electron pairs are between 2 atoms. So if I look at my oxygen atom that we've looked at before, it's got 2 bonds, so that's a bond order of 2. And the larger the bond order, in general, the shorter the bond. So an oxygen-oxygen single bond is going to be longer than an oxygen-oxygen double bond. This is a bond order of 1, and this is a bond order of 2. Since there's more electrons involved in that double bond, that's going to pull those atoms in closer together to make the length shorter. Next bonding property is the bond strength, which is how strongly one atom is bonded to another. And so this is equivalent to the energy required to break the bond apart in kilojoules per mole. And this table shows a bunch of different bond energies. And this is also connected very strongly to bond length. The shorter the bond length, the stronger the bond. And maybe it actually makes more sense to say that the other way. The stronger the bond, the shorter the length, because if there's a lot of electrons and there's a strong attraction between the 2 atoms, that's going to pull the atoms in closer, so you'll have a shorter bond length. And this shows that when we have, for example, let's compare the carbon bonds, the single, double, and triple. The carbon-carbon single bond is the longest, and so it's the weakest. It has the smallest energy. A double bond is slightly shorter, so it's stronger, and a triple bond is even shorter, so it's the strongest of the 3. And that's what we would see when any of the 2 atoms are the same. The higher the bond order, the shorter the length and the stronger the bond. Now, one place you're going to actually use those periodic trends in size that we learned in the last chapter is in comparing bond lengths. So you should be able to remember that trend and use that trend to compare bond lengths. So for example, if I want to compare a carbon-nitrogen bond to a carbon-oxygen bond to a carbon-fluorine bond, which one is the shortest? Well, we know based on the trend that our size decreases going towards the right of the periodic table. So fluorine is the smallest atom of oxygen, nitrogen, and fluorine that are bonded to the carbon. So the carbon-fluorine bond would be the smallest. So it's the smallest, and the carbon-oxygen is next biggest, and the carbon-nitrogen would be the biggest, or the longest bond. So you should really be able to do that all across the periodic table, knowing those trends in size. Brings us to Lewis dot structures or Lewis dot diagrams. And I've already shown some of these, but these are diagrams that we use to illustrate bonding in molecules. So when I drew the oxygen atoms with the lines between them and the lone pair electrons, that's a Lewis dot structure. And electrons are shown as dots, so those are lone electrons, lone pair electrons are shown as dots, and the bonds are shown as lines. And we follow a series of guidelines to draw these that are based on how many total valence electrons we have in a molecule and on filling the shells for all the atoms in a molecule. So let's go through some examples of those. Let's look at our guidelines for drawing Lewis structures. We start with a molecular formula, so let's look at the nitrate ion. That's NO3 with a -1 charge. So we start by counting up the total number of valence electrons by adding together the valence electrons of the atoms in the molecule. So we have nitrogen, which has 5 valence electrons. And then we have 3 oxygens, each that have 6 valence electrons. So that's 6 times 3, or 18 valence electrons. And then we have 1 electron for the charge. So that's 5 plus 18 plus 1, which equals 24 electrons. Now the goal is to put those around all the atoms in the molecule such that all of the atoms get their filled shell. So in terms of how we arrange the electrons, we start by putting the least electronegative element in the center. And so remembering our electronegativity trends, oxygen is more electronegative, so that means nitrogen is the more electropositive. So that atom goes in the center. We arrange the other atoms around it, just however we want to, connect with single bonds, and then we take that total number of valence electrons, subtract the bonds, or the electrons in the bonds, to leave us with how many electrons we have left over to give every atom a filled shell. So now we take those 18 remaining electrons that we have left, and we have to arrange them around our 4 atoms such that each atom gets its filled shell. So I usually just start on the outer atoms, and I just put pairs around those outer atoms. So that was 2, 4, 6, 8, 10, 12, 14, 16, 18. And you'll notice that the oxygens have filled shells, but the nitrogen does not. So we must need to do something different. And that's step 4, where if we're not able to fill those shells, we use lone pair electrons to make multiple bonds. So I'm going to take one of those lone pairs from one of those oxygens, and let's just make it this outer one, and make a double bond between that oxygen and nitrogen. And so give the other oxygens their 6 lone electrons. And now all the atoms have filled shells. But there's nothing that's special about this oxygen and this nitrogen that the double bond has to go there. We could actually move that double bond around. Before we do that, we're going to check the formal charge on each atom in this structure. And that's really our last step in determining whether this is a valid structure or not. So the formal charge is calculated by taking the number of valence electrons the atom started with, subtracting from it the number of unshared electrons around that atom in the molecule, and subtracting from it the number of bonds to that atom in the molecule. So if we do that for our nitrogen here, nitrogen started with 5 valence electrons. It doesn't have any unshared electrons around it in our structure, so that's 5 minus 0. And it has 4 bonds to it. So the formal charge on the nitrogen equals 1. And we draw that next to the nitrogen like that. So then these 2 oxygens, the formal charge is going to be 6 valence electrons that they started with, minus the 6 that are not shared in the structure, minus the 1 bond to give us a -1. So both of those have a -1 formal charge. And then this oxygen, the formal charge, is going to equal again the 6 valence electrons it came in with, the 4 unshared electrons in the structure, and the 2 bonds, so that's equal to 0, and so I would draw a little 0 next to that. So now there's certain rules that we have to follow when we assign formal charges. So there are some guidelines that we also have to follow for formal charges in order to ensure that we've got our structure as good as it can be. And first of those is that the sum of the formal charges on the atoms has to equal the overall charge of the molecule. So here we have a +1 plus a -1 plus another -1 that gives us an overall charge of -1, and we would show that by drawing brackets around this and the -1 there. So this structure does follow that guideline. We want the fewest possible atoms to have a formal charge while still filling all the shells, and we had to make double bonds, so there's not any other way we can fill the shells and get rid of formal charge, so this is the best we can do. We want positive formal charge on the central atom because it's more electropositive, negative formal charge on the outer atoms because they're more electronegative, and lastly we want opposite charges on the adjacent atoms. So our formal charges are as good as they can be, but as I said before, there's no special thing about this nitrogen and this oxygen that the double bond has to be there. Anytime you do have a double bond like that somewhere in your molecule, you can move that double bond around to draw what we call resonance structures. And let's go over what those are and what they mean. So what are resonance structures? These are equivalent Lewis structures with the same relative placement of the atoms, but different placement of the bonding and lone electron pairs. And you know that resonance structures are possible when you have multiple bonds, like we do in this nitrate. And the way you would draw those structures is by moving those multiple bonds around. So instead of having the double bond where I have it in that first structure, I could move it to between the other oxygen on the other side. And then I also move around the lone pairs, or it could be to the bottom oxygen. Those are all really equivalent structures. But what they represent is that electron density doesn't have to be located between any two atoms. And in fact, the electron density is actually spread out across all three of those nitrogen-oxygen bonds. What that means is that when we measure the actual nitrogen-oxygen bonds in this molecule, they're found to be equivalent to the length of 1.3 times a typical nitrogen-oxygen single bond. That tells us that that second electron pair is delocalized throughout the molecule. And the way we draw that is like this. We draw the dots to indicate electron density being shared between all three bonds. Lastly, whenever you can draw resonance structures for a molecule, you should, and the delocalization of the electron density that these structures signify has a stabilizing effect on the molecule. So let's do one more example. Formic acid, which is shown here, and the order that the atoms are drawn in indicates how the atoms are bonded to each other. And in fact, since this is an acid, this is the acidic proton, and that's always going to be bonded to an oxygen in an organic acid like this molecule is. And another thing is that when you have carbon in your molecule, it's going to be central. So we will do that. We'll put the carbon central, and the two oxygens that follow that carbon are bonded to it. And as I said, that one acidic proton is bonded to a hydrogen, or is bonded to an oxygen, and then the other hydrogen must be bonded to carbon to give him his octet. We had 18 valence electrons. We just used 8 in bonds, so we have 10 valence electrons left. Hydrogen is already complete, or has his filled shells, because he's got the 2 electrons in the bond, but the oxygens each need more. So there was 6 around that oxygen, 4 more here. That gave the oxygens filled shells, but the carbon is not happy. It's missing a filled shell. So we're going to again have to make multiple bonds. So we're going to take one of those lone pairs from the oxygen that doesn't have the hydrogen on it and make a double bond. So that oxygen now has 2 lone pairs, as does that one. And so that's the structure that gives everybody a filled shell. And we double check our formal charges. This oxygen has 6 minus 4 minus 2, so it's got a 0. This oxygen also has 6 minus 4 minus 2, so it's 0. Carbon has 4 minus 4 minus 0, so it's also got a 0 formal charge. And of course the hydrogens are all 0. So this is the best structure we can draw. I said before that if we have a double bond in a structure, we should try to move that around to make resonance structures. So let's do that and see if we do have any that are possible. So that would give us a structure like this. So we still have 18 total valence electrons. All of the carbons and oxygens have their filled shells, and the hydrogen has its 2 electrons to make its filled shell. But let's look at formal charge. This oxygen that now has the double bond has 6 minus 2 minus 3, so it has a +1 formal charge. And that's just not a good situation for an electronegative element. We also end up having on the upper oxygen, it's got 6 minus 6 minus 1 bond, so it's got a -1 charge. And that's better because an electronegative element like oxygen would prefer to have a negative formal charge, but we've got our opposite formal charges are not on adjacent atoms. And so that's one bad thing, but also we have a +1 formal charge on the very electronegative oxygen. So both of those things make this a bad structure. So this is not a valid Lewis structure. Structures are only valid Lewis structure. Okay, so to finish up, I just want to cover the exceptions to the octet rule, and we already know the one about hydrogen. It only needs 2 valence electrons to have a filled shell. Boron and beryllium are okay with less than 8, but they can have 8. And then there's certain elements in the 3rd row and beyond that can have more than 8 valence electrons in their valence shell, meaning that they exceed the octet rule. And examples of this are phosphorus, sulfur, chlorine, and iodine. So again, this is covalent bonding, Lewis structures. Do some practice problems, and thanks for watching.